Greetings, math friends. This is AP Calculus section 5.3, day 3 notes. So today we are going to start with a particle problem. It says the velocity function in meters per second is given for a particle moving along a line. Find the displacement of the particle and the distance traveled by the particle during the given time interval. So first of all, I want to clarify the fact that displacement and distance traveled are not the same thing. Distance traveled by the particle is the positive distance added to the negative distance, right? So it's the positive distance plus the absolute value of the negative distance, so it's like the total movement. Whereas displacement is just the change in position of the particle from its starting point to its ending point, okay? So those are going to be two different things that we are going to find, all right? And we're doing this for this velocity function, t squared minus 2t minus 8 on the interval from t equals 1 to 6. So the first thing is we need to know when our particle is stopped, because that is going to help us calculate our distance traveled, so we know when it's traveling in the forward direction and when it is traveling in the backward direction. And so we know that our particle is stopped when our velocity is 0. So I'm going to take my given velocity function and I'm going to set it equal to 0, and I'm going to solve for t. And this equation can easily be factored. Two numbers that multiply to make -8 and add to make -2 are going to be -4 and +2. So t minus 4 times t plus 2, and that means that t equals 4 and that t equals -2. Now, obviously, we're talking about time, so -2 does not make any sense. So the only good answer we have here is that our particle is stopped in our interval from 1 to 6 at t equals 4 seconds. Okay, so let's begin by trying to find the distance traveled by our particle. And remember, I said that distance traveled, let's write this down, is the positive distance added to the absolute value of the negative distance. And just a reminder, the particle changes direction when it is stopped. So that's why we figured out when it was stopped first. All right, so we need a position function for our particle, right? We have the velocity, so our position function is just going to be the integral of our velocity function. So our s of t then is going to be the integral of our v of t. So it's going, or the antiderivative, if you will. So our first term will be 1/3 t cubed. Our second term will be negative t squared. Our third term will be negative 8t. Okay? And it is our position function that we are going to use to calculate our distance traveled, because we know that the particle's moving in one direction from 1 to 4 seconds, and then it stops, and then it changes direction, so it's moving in a different direction from 4 to 6 seconds. So we need to calculate the particle's change in position from 1 second to 4 seconds, and then we need to calculate the particle's change in position from 4 seconds to 6 seconds. And the way that we find these is by plugging 4 second and 1 second into our position function to see where the particle is at that time. So again, this is going to be the absolute value of s of 4 minus s of 1. Which, when you plug 4 in to our position function, our s of t, you're going to get 4 cubed, which is 64, times 1/3, minus 4 squared, which is 16, minus 8 times 4, which would be negative 32. You do the math there, and you end up with negative 26 2/3. And you do the same thing. You plug 1 in. 1 cubed times 1/3 is 1/3. Minus 1 squared would be minus 1. Minus 8 times 1 is going to be minus 8. So we end up with minus here, negative 8 2/3. And then, of course, we can chop our minus a negative here. So we end up with negative 26 2/3 plus 8 2/3, which gives us negative 18. But the absolute value of negative 18 is 18, right? Now we are going to do the same thing on the interval from 4 to 6. So first I will do s of 6 minus, and then s of 4, which we already have a value for, so that's helpful. And s of 6, when I plug 6 in, 6 cubed times 1/3 minus 6 squared minus 8 times 6, that ends up being a value of negative 12 minus, and again, negative 26 2/3 minus a negative, chop. We add negative 12 plus 26 2/3, and we end up with positive 14 2/3, which the absolute value is positive 14 2/3. And so finally, our total distance traveled is going to be these two distances added together, which gives us a total of 32 2/3 meters. So that is our total distance traveled by the particle. But displacement of the particle, we're going to calculate differently. Displacement of the particle is the change in position from its starting point to ending point. Okay. And this we are going to calculate using the definite integral of the velocity. Okay, so again, this is how we are going to get our displacement of our particle. So the definite integral of the velocity is going to be the integral from 1 to 6 of our velocity function, which is t squared minus 2t minus 8 dt. So of course, when we integrate that, we already know what we get because that was our position function. That is 1/3 t cubed minus t squared minus 8t, and we're going to evaluate this from 1 to 6. So then we go ahead and we plug 6 in, so 1/3 times 6 cubed minus 6 squared minus 8 times 6. And we are going to subtract from that what we get when we plug in 1. 1/3 times 1 cubed minus 1 squared minus 8 times 1. And we've already done some of this math, right? But here we end up with 72 minus 36 minus 48. And if we keep going, then we end up with negative 1/3 -1 and -8. But then when we go ahead and we distribute that negative sign through, we're going to have 72 minus 36 minus 48 minus 1/3 plus, my apologies, error here. This should be -1. So minus a -1 here is going to be +1. And minus a -8 is going to be +8. So then we go ahead and we add all those values together, and we find that we end up with a displacement of our particle being -3 1/3 meters. So our particle moved in the negative direction 3 1/3 meters from where it began. Okay? Since we are talking about integrals, I want to take a moment and I want to backtrack to when we calculate our distance traveled. And the way that we did this was the way that we did it earlier in the school year, where we plugged our starting point and ending point in the positive direction into the position function and subtracted, and then likewise in the backward direction, and then we added the absolute values of those two. But I did want to point out that we could also do our distance traveled using integrals. It's just that we need to know when the particle is moving forward and when the particle is moving backward so that we can take the opposite of the integral, right? So in this case, hopefully you can see that when the particle is moving from 1 to 4, because we ended up with a negative value in our absolute value bars, we know that this was backward movement right here. Right? And we know this because we ended up with this -18. And we know that from 4 to 6, our particle had to be moving in the forward direction because we had a positive 14 2/3 here. Well, again, we could also calculate this. So here's our or. We could also calculate this as saying our distance would be equal to negative, or the opposite of the value of the integral from 1 to 4 of v of t dt plus the integral from 4 to 6 of v of t dt, right? So basically putting the negative in front of the first integral will negate the negative sign that you would get from the value of that integral, right? But in order to be able to do the distance traveled with integrals instead of doing it with the absolute values of the position function, you do need to know ahead of time which one is your forward direction and which one is your backward direction. Moving on to example 2. The acceleration function in meters per second squared and the initial velocity are given for a particle moving along a line. Find the velocity at time t and the distance traveled during the given time interval. All right, so let's begin by first finding our velocity function. So again, if we have our acceleration function, we know that velocity is the antiderivative of acceleration. So we know that our v of t is going to be equal to, for the first term, it will become t squared. I will need a 1/2 to undo the squared in front. My second term will be 4t, and then of course I'm going to have a plus c. Now I was given the fact that v of 0 equals 5, so I can use that to solve for c. So basically when I plug everything in here, when I plug 0 in for my terms, I end up with the fact that c equals 5. So my velocity function is 1/2 t squared plus 4t plus 5. And this is our equation for velocity at time t. Okay, so now our second step, this was our first step. Our second step in this problem is going to be to find our position function. And of course, now that we have our velocity function, we're able to find our position function because it would be the antiderivative of velocity. So our position function, we will call this our S of t, is going to be equal to, now I have to integrate each term. So the first term will become t cubed. I will still have the 1/2 in front, but then I also have to multiply by 1/3. So 1/2 times 1/3 is going to make the coefficient 1/6, t cubed. My second term is going to become t squared. I still have the 4, but I have to multiply by 1/2. Half of 4 makes my coefficient 2. And then my third term, the 5, is going to become 5t, right? And we can use this to find the distance traveled on our interval from 0 to 10 seconds. Okay. In order to do that, though, of course, we need to know when our particle is stopped, right? Because we know that when it's stopped, it's changing direction. So that's going to be our next step here. I'll call it step 3. Our particle is stopped when our velocity is 0. So if we set our velocity function equal to 0, remember our v of t is equal to 1/2 t squared plus 4t plus 5. If we set that equal to 0, I'm not a big fan of trying to solve or factor when a is a fraction, so I'm just going to go ahead and I am going to multiply this whole thing by 2. You know, at the very least, it's going to give me integers to work with instead of that fraction. So 2 times 0 is still 0, but then this is going to become t squared plus 8t plus 10. And now you can easily see that if I tried to factor two numbers that multiply to make 10, but add to make 8, I'm not going to be able to find a pair. So I'm going to have to solve this by the quadratic formula. Okay, it's not factorable. So t is going to be equal to the opposite of 8 plus or minus the square root of 8 squared plus -4 times 1 times 10, all divided by 2 times 1. And then you grab your calculator and you do the work underneath the square root. 8 squared is 64. 64 minus 4 times 1 times 10 is 40. 64 minus 40 is 24. So I end up with t equals -8 plus or minus the square root of 24 divided by 2. And then, of course, you grab your calculator and you solve for t, and what you get here when you do the math on your calculator is that t is approximately equal to, and of course we're going to get two values here because of the plus or minus in front of the square root. The first value that we get is -1.55 seconds, and the second value that we get is -6.45 seconds. Well, this doesn't make any sense for us because on our interval, we have from 0 to 10 seconds, and these are negative times. So since we didn't have any answers within our interval, what this tells us is that our particle does not stop on the interval from 0 to 10. Big news. Okay, the particle does not stop on the interval from 0 to 10. Okay, well, how can we use that then to find our distance traveled? Okay, because our particle's never at rest, it never changes direction. And in this case, it's always moving in the forward direction. Okay, so again, let's write this down. Because the particle is never at rest, it never changes direction. In this case, it is always moving in the forward direction. Okay, and so because of this, our distance traveled and our displacement will be the same. And we can calculate our distance traveled then using one integral. Okay, so our distance then is going to be equal to the integral from 0 to 10 of our velocity function, which is 1/2 t squared plus 4t plus 5 dt. And we already know what that is because we already found our position function. That is 1/6 t cubed plus 2t squared plus 5t evaluated from 0 to 10. And so when we go ahead and we plug in 10, we get 1/6 times 10 cubed plus 2 times 10 squared plus 5 times 10. And if we were to plug in 0, because all three of our terms contain t, all three of our terms would be 0. So we end up with, when we do the math, 416 2/3 meters. That is our total distance traveled. Example 3 says, suppose that a volcano is erupting and readings of the rate r of t at which solid materials are being spewed into the atmosphere are given in the table, where t is measured in seconds and the units for r of t are in metric tons per second. Okay, so part A says, give upper and lower estimates for the total quantity Q of 6 of erupted materials after 6 seconds. Okay, so since we have a table of values, basically this exercise is going to take us back to our finding the area under the curve using rectangles technique, because we don't have a function to work with. All we have is a table of data. So the first thing that I'm going to do, I am going to make two different graphs, the same graph twice basically, but one of them I am going to use to find my upper estimate, and the other graph I am going to use to find my lower estimate. So I am going to build a coordinate plane for my data. And I need to go from 0 to 6 on the x-axis. And I need to go from about 0 to 60 on the y-axis. And I can certainly mark off the 5s on the in-between there. Okay? And I am going to just repeat this exact same coordinate plane over here. Okay. And so now when I plot my points from my table, using the data that I am given, it's going to create a curve. All right, so let's take a look at what we get. When t is 0, I'm at 2. When t is 1, I'm at 10. T is 2, I'm at 24. T is 3, I'm at 36. T is 4, I'm at 46. T is 5, I'm at 54. And when t is 6, I am at 60. So I have something that looks like that. It's got a little bit of a curve to it, right? And I'm supposed to give an upper estimate and a lower estimate. Now, when we're using rectangles, remember that we have left endpoint rectangles and we have right endpoint rectangles. So in this case, if we're supposed to be giving an upper estimate, then we are going to be using right endpoint rectangles for our estimate. So my right endpoint rectangles are going to look like this. And as you can see, I'm going to have that overhang above the curve, which is why, because my function is increasing, right endpoints are going to give an overestimate, right? And so now I'm just going to try to find the area of all of those rectangles, which, again, I just have to do the math here because I know that the bases of all of those rectangles are 1, so I just have to try to, use the heights there and calculate my value. But all of these values come from our table, so our Q here is going to be approximately equal to, height of the first rectangle is 10, and again, it's 1 times everything because the base of every rectangle is 1, right? So height of the first rectangle is 10, height of the second one is 24, height of the third one is 36, height of the fourth is 46, height of the fifth is 54, and height of the sixth is 60. And you add all those numbers together and you multiply by 1, and our upper estimate here is 230 tons. Okay, that is our upper estimate. Now we're going to do the same thing, but this time we are going to use left endpoints for lower estimates. So once again, I need to plot my points first. Same points that I plotted before. So 0, 2, 1, 10, 2, 24, 3, 36, 4, 46, 5, 54, and 6, 60. So once again, there's my curve. But this time, when I use the right endpoints for my rectangles, my first rectangle will be there, second there, third, fourth, fifth, and sixth. And so this time, with left endpoints, my lower estimate, you can see, is obviously going to be a lower estimate because I have that space underneath my curve there that's not being accounted for, basically, right? And so when I do this time my calculation for my Q is going to be approximately equal to 1 times, but this time my endpoints, or my heights, are going to be 2 plus 10 plus 24 plus 36 plus 46 plus 54. And when I add those all together, I get a lower estimate of approximately 172 tons. Okay. So again, you may want to put a little note here that my lower estimates came from left endpoints, and that my upper estimates came from right endpoints. And this is because my function was increasing. That will always be the case when your function is increasing. If your function is decreasing, then those two things switch around. And of course, we built 6 rectangles because they wanted us to find Q6, right? So our delta T here for these problems, I probably should have written this as down first, but was 6 minus 0 divided by 6. And that's how we knew that the base of each rectangle should be 1, right? But that was pretty intuitive, knowing that we needed to build 6 rectangles, and we went from 0 to 6 on our x-axis. All right, so now part B asks us to use the midpoint rule to estimate Q6, okay? And there's a catch to this. If we want to use the midpoint rule, we can't use 6 intervals because we don't have data for the value between t equals 0 and t equals 1, or the value between t equals 1 and t equals 2. So let's write that down. We can't use 6 intervals because we don't have midpoint data between t equals 0 and 1, or t equals 1 and 2, etc., right? So the best we can do is divide our area into 3 rectangles using the data we have. Okay, so our delta t then is going to be 6 minus 0 divided by 3, which tells us that, since this is the number of intervals is 3, that the base of each of our rectangles is now going to be 2 units. So we are going to make our graph yet one more time here. And again, I am just plotting the points from the data table given above. Zero, 2, 110, 2, 24, 3, 36, 4, 46, 5, 54, and 660. Okay. And so now, if we are creating a base of 2, right, then this point right here is going to be our midpoint for our first rectangle. And this point right here is going to be our midpoint for our second rectangle. And this point right here is going to be our midpoint for our third rectangle. Sorry, I perhaps should have drawn my curve in a different color there. Let me do that real quick. There we go. Okay. So there we have our midpoint drawing with 3 rectangles. And so we are approximating Q6 using the midpoint rule. So Q6 is approximately equal to, this time it's 2 times. And then our midpoints are the value of the function at 1, the value of the function at 3, and the value of the function at 5. So when I plug those numbers in, it is 10 plus 36 plus 54. Multiplying that sum by 2, 2 times 100 gives us approximately 200 tons. And we can assume that that is a better estimate than what we found in Part A, because our upper estimate was 230, our lower estimate was 172. 200 is between those values, so even though we could only use 3 rectangles instead of 6 for our midpoint rule, we still get a closer estimate here to the area under the curve.